They have peptidoglycan, but very thin. So, thin peptidoglycan. That's the second one. Now, on the top, what you have, they have another layer somewhere here. Somewhere here, another layer. That's called the inner layer, an outer layer. So you have another layer right here. Then above the top, what you have, something showed up, LPS, lipopolysaccharides. This one with a very heavy percent, lipids A. So you see the difference between these. You can draw your notebook. You understand it very well. Now what's the story? There are two theories described about that. Number one is cell wall theory. What is the cell wall theory? You heard about it all the time. Gram-positive bacteria have a heavy peptidoglycan. Gram-negative bacteria has a thin peptidoglycan. So what happened is, when you do the staining for crystal violet, for gram iodine, for gram-positive bacteria, that heavy peptidoglycan can hold on that. So when you do the 95% alcohol decoloration, it stays there. It did not remove them. So finally, you do the counter stain. That saffron color did not show up because the crystal violet is contained by heavy peptidoglycan. So gram-positive bacteria, why the stains blue to purple? This color is crystal violet color. Now, in other words, for gram-negative bacteria, this peptidoglycan is very thin. So you put a crystal violet, you put a gram iodine, that thin peptidoglycan cannot hold on. So when you do the decoloration, put 95% of alcohol, it's all washed off. So ideally, nothing there, no color there. What we do? We need to put something there. We do the counter stain with saffron. And the saffron is pink to red color. So that's why gram-negative bacteria is pink to red color. And this is actually saffron color. So that's the first thing. So cell wall theory said very simple. Heavy peptidoglycan hold on crystal violet during decoloration process. That's very simple for cell wall theory. That's the first thing. This is you heard about. And I have another theory. It's called the lipid theory. What is lipid theory? Again, we go back to see the structure. Gram-positive bacteria, cell membrane system, peptidoglycan, teichoic acids. Gram-negative bacteria, double layer, and you have a lipopolysaccharides. The major component is lipids A. So what is going to make the difference? Gram-positive bacteria, the lipids amount is somewhere less than 5%. And the gram-negative bacteria, the lipids amount is about 10 to 15%. Why it is important? Lipids dissolved in alcohol. You put a crystal violet, you put a gram iodine, its zinc peptidoglycan cannot hold on, plus you have 15% of lipids. The lipids will be easily to be interacted with 95% alcohol, and they all removed off. It's called organic reagent. What is the definition for an organic reagent? It's very simple. They could be dissolved in alcohol. And the lipids is one of that. That's the reason. In other words, for gram-positive bacteria, the lipids amount is very less than 5%. They cannot be washed off with alcohol. At the same time, they reacted with the alcohol, neutralize the alcohol, and let peptidoglycan can hold on the gram crystal violet much stronger. So, said very simple, lipid theory, 10 to 15% of the lipids of gram-negative bacteria make decorrelation easy after lipids dissolved in 95% alcohol. So that's just two theory about gram-negative bacteria, why it stains pink, red, and the gram-positive bacteria, why it stains purple to blue. Cell wall theory and the lipid theory. So based on the theory we write on the blackboard, you should keep in mind, gram stain, you have to use very young culture. It has to be less than 18 to 24 hours. And ideally, there should be a growing bacteria. Why? Because gram stain is based on the cell wall structure. And the young bacteria, fresh bacteria, they're just building the cell wall structure, or they're building cell wall structure, it is stable. If it's very old culture, let's say more than 48 hours, 78 hours, they already start to cracking down. The peptidoglycan is already being started to loosen. What happened? Everything will stain gram-negative, no matter what. That is called gram variable stain. So we say we have to use very young culture, otherwise we'll have gram variable stain. Gram variable stain, which means everything stains like gram-negative, no matter what. So I give you a very easy example. Staphylococcus aureus is gram-positive bacteria. Then, if you use a culture which is already 72 hours old or 3 days later, then no matter what you do, at the end of the day you find that it is pink, because it's already being started to die. And the peptidoglycan is already started to cracking down. Okay, so that's the reason. And you're not going to differentiate between gram-positive and the gram-negative at that moment. So, this is very important. We talk about the gram stain, and the procedure is important, the time is not important. Using a very young culture is important. Okay, so that is the key. Next one, I want to finish talk about the acid-fast stain, then we let you off. So we talk about the gram stain. We'll practice in the lab, and then we want to talk about some of the special stain. There is actually 3 special stain, which is indosperm stain, flagella stain, and acid-fast stain. Those are not going to be categorized into positive or negative because it's specific for targeted bacteria. So first of all, we want to talk a little bit acid-fast stain. But why we want to talk about the acid-fast stem? Because we just talk about the history of microbiology. We talk about the TB, tuberculosis, and acid-fast stem, we can do that. Acid-fast stem, it is specifically for a group of the bacteria called mycobacteria. B-A-C-T-R, mycobacteria. Mycobacteria has a risk group, tuberculosis. Tuberculosis. But they also have another mild species, leprosy. Microbacteria, originally it's coming from soil. Lots of the species of microbacteria will cause bone deformation and the results hunchback. Is there a cartoon movie called a Hunchback what? There's a cartoon movie there. It's a hunchback, and it looks like contaminated with microbacteria. Now, originally, where they come from? Raw milk. And it's a big debate in the West Virginia area where we should eat unpasteurized raw milk. It has a high nutrition there, but unpasteurized milk will result a high amount of microbacteria, could cause bone deformation. Okay, debone, what we said. That's microbacteria. But tuberculosis, we already mentioned. It's a severe infectious disease. Now, what's the characteristics of this microbacteria? This bacteria has a high amount of long-chain unsaturated fatty acids. It's called mycolic acids. Because of these mycolic acids, it will make a very special cell wall. We call it a waxy cell wall. Like your floor of your house is waxed. Therefore, using basic dye, simple stem and gram stem, it doesn't work very well. So what we have to do, we need something to penetrate this waxy cell wall. We need to rely on a dye called carbon fusion. It's a red-pink color. Not only for that, we need to rely on a heat. So we call it a heat steaming. We will show you in the lab how to do that. So carbon fusion with heat steam. And finally, we have to do kind of like a counterstain. We counterstain with methylene blue. So what happened? The results will be very much like the picture showing. Microbacteria is purple color to red color, and the background is blue color. The blue color is methylene blue. And if you have a patient which has TB, has tuberculosis, usually what they do is they do fever measurements, the temperature, you have a fever, you have a productive coughing about 3 weeks, you have a cloudy area in the lung area, then they will get you sputum sample to do the acid-fast stain. If you see a positive acid-fast stain, which means this guy is presumptive TB, so you have to do antibiotics immediately. Because TB is growing very slow. and they need to grow in a transport medium and transfer to the reference lab. I believe in West Virginia area is in Lexington. In the south part is in Georgia, Atlanta. So in the reference lab, they're gonna finally to do the cultivation and do the identification, but it took 2 days for microbacteria to grow because their lag phase time is extremely long. It's not like E. coli. The E. coli can grow 6 to 12 hours. Microbacterial tuberculosis took at least 48 to 72 hours. So that is what we call acid fast state. We used to have the bacteria string in the lab, we can practice, but a couple of years later it's died, so we can only talk right now. But we have another one, which is we call the practice, which is endospore stem, and very similar to that. We will introduce you how to do the heat steam. Okay, so we will do this next week, and we will talk about these next week. Thank you.